Push that rock here with Simpson math. We're going to vertically translate and also reflect trig functions. So I've prepared for us here an apparent sinusoidal wave, y equals sine of x. And one of the things we want to be able to do is just vertically translate it. So if I were to want to graph y equals -2 plus sine of x, which could be rewritten as sine of x minus 2, then what I would do is I would put inputs in, like pi, put pi in, sine of pi is 0, and then subtract 2. So for every given input, the output is just lowered by 2. That means we just lower the graph by 2. So this point, which is at 0, lowers by 2 units. This point, which is at 1, lowers by 2 units. 1 minus 2 is a -1. 0 lowered to -2, this 0 would lower to -2, and -1, this output at -1 would lower, -1 minus 2 is a -3, so it would lower to -3. And then we have the sine wave, and you see that it's clearly just been lowered by 2 units. We could also raise it 2 units or 3 units or however many units you want by just adding that amount to the function. Now, another thing I want to cover in this short video is how to reflect it over the x-axis. So if I were to reflect the graph over the x-axis, all I have to do is multiply it by a negative. Because what happens if you multiply by a negative? Whoa, that's pretty thick ink there. Okay. Is now when I put in a value like 3 pi halves, when I put in an input of 3 pi halves, sine of 3 pi halves is a -1. But I have the negative on the outside, and negative of a negative becomes a positive. So this negative becomes a positive. And any positive would become a negative, but any 0 would stay the same. Negative of 0 is still 0. So all of the zeros would stay the same. And so we see we just have the sine wave reflected over the x-axis. Notice that the point that was 1 unit below the x-axis is now 1 unit above. So it's like the x-axis is a mirror and the reflection is equidistant from the mirror inside the mirror. So you have, here's outside the mirror, you're looking at yourself in the mirror, you're a foot away, your image appears to be a foot behind the mirror. But if you're on the mirror, if you're a fly that's landed on the mirror, the image looks like it's on the mirror as well, and that's why the zeros don't move. So that's reflection. Now you can combine these two things. I could reflect and then add something to it. So if I were to try to graph something like y equals 1 plus a negative, which is the same thing as minus sine of x. So this is the same thing as 1 plus a negative. So I'm just taking 1 and adding it to this. That means I'm just adding 1 to the reflected graph, so I'm going to lift everything up 1. So the reflected graph would go up 1. This unit, this point here would go up 1 unit. This point would come up 1 from -1 to 0. This 0 would go from 0 to 1. This 1 would go from 1 to 2, because 1 plus 1 is 2. Whoa, what was that? And then this 0 would go up to 1. And so my reflected graph has been shifted up 1 unit, and that's y equals 1 minus sine of x. There's one other type of reflection, and that's reflection over the y-axis. And in sine's case, it's no different from reflecting over the x-axis, okay? And why is that? Well, let's take this reflected red graph and let's extend it. Okay, so if I extend the red graph, if I continue the pattern is like so. So it would go up to here, and then to here, and then to here, and then to here. Well, notice that this point right here, wait a minute. Yeah, this point right here on the original graph is 1 unit from the y-axis, and now it's 1 unit on the other side of the y-axis. And this point, well, not 1 unit, misspoke there, 1 tick mark, okay? The tick mark units though are pi halves, so it's pi halves unit away from the y-axis, and now it's pi halves units on the other side. And this one is 3 tick marks, which is 3 pi halves units away, and look, it has a mirror image over here. So when I reflected the graph over the x-axis, I was simultaneously reflecting it over the y-axis. That's actually a cool attribute of the sine wave and its reciprocal, and of tangent and its reciprocal. And functions that have this cool attribute of reflecting over one axis is the same as reflecting over the other axis are called odd functions. And so that gives us one of our identities, the odd identities. That tell us that, hey, reflecting sine over the y-axis is the same as reflecting it over the x-axis, and the same for its reciprocal, and the same for tangent, and it's also true for tangent's reciprocal, cotangent. So if you reflect any one of these functions over the y-axis, you've also reflected it over the x-axis. But if you reflect it over the x-axis, you've also reflected it over the y-axis. And this will be helpful when we're verifying identities as well. If we have some tricky negative inside the argument, for all of these odd functions, we can just kick the negative out, because negative of the function is the same as sine as the function negative of its input. And so that will be very helpful later on. So we'll need these odd identities, put those in your notes. And that's my video on translation and reflection. In our next video, we will translate horizontally, which on trig functions is called a phase shift. Math made simple, Simpson math.